the review of the major points, and then we will start solving problems. It usually takes like 15 minutes to review. So this exam is based on chapter 9, 10, and 11 up to section 4 included, right? So two-dimensional collisions are not going to be on the exam, right? One-dimensional, yes, but two-dimensional collisions, we will look at a couple of examples after the exam. Okay, so let's start. First, I want to look at scalar or dot product. Right. So what is that? So if you have, for example, two vectors, right, vector A and vector B, and let's say, and again, how to find the angle, the right angle between two vectors? You need to position their tails at the same point, right? Tails of both vectors at the same point, and then the angle, which is less than 180 degrees, is the correct angle to calculate now scalar product, and after the exam we will introduce vector product, right? Every time the rule is exactly the same, how to find the correct angle. So this is theta, and then a dot product, A dot B, it's a magnitude of vector A times magnitude of vector B times cosine of angle between them. Cosine of angle between them. It's one way of finding, right, if you know magnitudes and angle. But what if vectors are given in the component form? Ax, Ay, Az, Bx, By, Bz. In that case, A dot B, it's Ax, Bx. You just multiply corresponding components and add them up, right? You've done it already many times. Ay, By, and plus Az with Bz. Right. So it's a first, right? Scalar or dot product. Then, pretty much this part of the semester we spent developing and using a new approach to solve problems, right? Instead of using vectors, we decided let's move to new quantities, to scalar quantities, and then dealing with scalar quantities is so much easier, right? So we moved to the energy approach. So instead of Newton's second law, we introduced which principle we used instead of Newton's second law in our energy approach? It's a work kinetic energy principle. That's what we derived from the Newton's second law, right, at the beginning of chapter 9. So now let me do that. So energy approach, well, let me label it energy approach. So instead of Newton's second law, F equals ma. By F I mean the net force. We, after some manipulations, introduce work kinetic energy principle. W, which is work, equals to the change in the kinetic energy, right? So which we call as the work kinetic energy principle, right? So now that's what we use for quite some time to solve problems, right? Yeah, I'll probably leave, right. It's a work kinetic energy principle. Then, and of course, kinetic energy we introduced, right? The 1/2 mv squared, right? And we also introduced work, the idea of work, right? First, we introduced in a more general form as an integral. We have to integrate force over what? Over which variable in order to get force? In order to get work? Position, x. Right? You need to look at the force in space over some displacement, right? So we integrated f dx, so from some x1 to x2. That's how we introduced work, right? Of course, we did not, as I promised, we're not going to do any integrations. So as a result, if force is not constant, what can be used to calculate the work? Area. Of course, you need to calculate area. You need to plot integrand versus variable of integration, right? So let me write area under f versus x. Right? So you can have, for example, like if you plot f versus x and let's say you have some arbitrary curve, which is not constant. Force is not constant in this case. So let's say this is your initial position, and that is your final position, up, lower and upper limit. Right? So that area is work. We've solved quite a few problems, right? So that's the area we need to calculate. Let me frame this as well, because it's very important, right? Definition of work. And it's a scalar function. Then, we simplified, of course, this expression. If force is constant acting on the object, what did we use to calculate work done by this constant force? Remember? It's a dot product. Dot product is involved. Scalar product is involved. It's just F dot S. Instead of X, we use S. But S is just displacement here. X is a displacement, right? So if F is constant, work can be calculated as the dot product F, force, and the displacement. And of course, explicitly, we can write it's a magnitude of F, magnitude of S, times cosine of angle between them. And again, you need to use that rule how to find the right angle between these two vectors. Right? F, S, times cosine of angle between them. Okay, so let me frame this as well, because most of the time that's what we use. We use this formula, dot product, scalar product, or the area under the curve, right? So these are two ways of calculating work. Yeah, okay, now let me separate this part. It's a second section. Maybe I should label it. So it's a first part, this is second. Right, so we made a transition to the energy approach, right? And then we started introducing potential energies. Potential energy can be introduced. Which force can lead to the potential energy? What's the name of that force? Those forces. What are the name of those forces? Conservative, right? If a force is conservative, we can introduce a corresponding potential energy. Gravitational force is a conservative force. We can introduce potential energy mjy. Spring force is a conservative force. We can introduce potential energy 1 over 2kx squared. Okay, so let me write if F is a conservative force. Again, the name conservative because this force allows us to introduce conservation of mechanical energy later on. Right? If force is conservative, right, we can introduce potential energy. We can introduce PE stands for potential energy, right? Right. So, for example, F gravitational equals to mg, and of course we can introduce potential energy. U equals mg y. And whenever you introduce gravitational potential energy, what do you have to show every time in the picture? The reference level. The reference level must be shown because this y is a distance measured from the reference level, right? To the point where the object is. Of course, perpendicular distance from the level to the point. Right. And then spring force minus kx, Hooke's law. Corresponding potential energy 1 over 2 kx squared. Maybe I should add the subscript g, gravity. And here USP, spring, it's a 1 over 2 kx squared. Let me frame them. And maybe I'll frame them all together. Now, yeah, and also, when you introduce potential energy, what's the relationship between the work done on the object and these potential energies? Anyone remembers? Although we did not use it quite often. Let me just write it just in case. Work equals to the negative change in the potential energy. We haven't used it much, just a few times. Okay, so we introduced potential energies. Let me separate this part. So now we have these type of energies. And now we can introduce conservation of mechanical energy. Immediately after this, naturally, conservation of mechanical energy follows. All right. Let me put this as number 4. Right. If there are no losses, if there are no losses, no friction forces, for example, friction, air resistance, right? If there are nothing like this, all the forces are conservative, we can use conservation of mechanical energy. If there are no losses in friction in the brackets, right? So then we can use conservation of mechanical energy. Conservation of mechanical energy. So you just compare total mechanical energy at some initial point with the total mechanical energy at the final point, right? Kinetic plus potential, and so on. We've done it already many times. Get it back and right. No. So K initial plus U initial equals to K final plus U final. Okay, let me frame this. Because most of the time solving problems using energy approach, we used either work kinetic energy principle or conservation of mechanical energy, right? Then, next, what if we have some losses in the system, some object slides, kinetic energy changes, potential energy changes, and let's say we have friction, like box sliding along the inclined plane in the presence of the friction force. Let me put 5. If there are losses, let's say if there are losses, friction, for example, right? Non-conservative force, friction force. So in that case, we derived again. To this expression, we just need to add work done by this friction force, non-conservative force. Right, so we wrote it in this way. Final total mechanical energy equals to initial total mechanical energy plus work done by the friction force, which is a non-conservative force. Let me frame this. We used it also a couple of times, right? A couple of problems. Okay, so after this, we said, yeah, we explored almost everything which is possible in the energy approach. We introduced all the tools that we need, mainly work, kinetic energy, potential energy, and of course, work, kinetic energy principle, and conservation of mechanical energy, right? And then we decided, okay, let's go back to vectors. We started looking at the Newton's second law again. We rewrote that Newton's second law in the most general form, right? And we introduced linear momentum, right? Just new stuff, which we just finished discussing in our class, right? So now it's a 5. Now let me put section 6. All right. So if you have, for example, some object, right, of mass m, moves with velocity v, and of course we can introduce linear momentum, right? Linear momentum p and product of the mass and the velocity. It's a vector now, right? We're back to vectors. Of course, that will be linear momentum. Right, it's a linear momentum. Then, Newton's second law, we rewrote. So first we have net force equals on the object leads to the acceleration, mass times acceleration. Right? And we rewrote it using this linear momentum in this form. Net force acting on the object leads to the change in the potential, or change in linear momentum, rate of change of the linear momentum. Again, this is the most general form. This is truly universal law. You can apply it to any system, of course, classical mechanical system, at any point of the universe, at any moment of time, and that is correct. So this is universal law. Right, so now let me frame it. Okay, so general form of Newton's second law. Right. It should have been framed with red, but I have played it like red, so I decided to use blue. All right, next. Yeah. After that, we introduce impulse. Right? We introduce impulse. Let me put a small bullet and impulse. So we introduce impulse. We use letter J, and we introduce impulse. Do you remember which way we introduced impulse? It's easy to recall. If you remember the definition of work, idea is very similar, but here we integrate in space, right, over x, but now we have to integrate over time. Right? Space, time, yeah, they goes together. Right? So here we integrate over x, and now it's an integration of force over time, right? F dt from some initial moment of time to some final moment of time. Right? So that's the definition of impulse. Right? And again, we're not doing integration in this class, so in order to calculate impulse, we calculated area under the curve. But now we have to plot what? Here we plot force versus displacement. Now we have to plot force versus this variable of integration, which is time. So now we need to know information about how force changes in time. So now I will write it's an area, and let me plot F versus time. Let's say we have some arbitrary curve. This is initial moment of time, that is final moment of time, and of course the area between these moments of time. So this area, that's what impulse, right? And we solved quite a few problems using this principle. Next, yeah, and of course when we introduce this impulse, we introduce also momentum principle, which is similar to the work kinetic energy principle. So now, let me put a small bullet. Momentum principle. So J equals to the change in linear momentum. Again, idea is the same like work kinetic energy principle. Here, work allows us to calculate how much of energy was added into the system. So force acts on the system, so as a result it might go faster or slower, right? So, but from the energy approach, if work is positive, basically we just dump additional energy into the system. As a result, kinetic energy goes up. But if work is negative, basically you're like extracting energy from the system, dumping in the outside world, and as a result, kinetic energy goes down. Here, it's very similar. Impulse, it adds now linear momentum into the system, or takes linear momentum out of the system. So linear momentum can go up or down. So pretty much the same problem can be solved using either this or that. It depends what is given. If you know how force changes in time, of course this will be easier. If you know how force changes with position, of course work kinetic energy principle. So now we have basically like 3 ways of solving problem. You can use Newton's second law, like we've done at the very beginning. Then you can use work kinetic energy principle, or you can use this momentum principle. If, for example, you want to find the velocity, final velocity after force acted on the system over some distance over some period of time. Now let me separate this part. And now the last part, very recent collisions. Let's refresh collisions. So now it's chapter 11, and this, which section? It's a 7, right? Section number 7. Now let's look refresh collisions. First, let me just draw some arbitrary picture of two balls colliding, for example. Let me do it here in this corner. Let's say initial situation. Let's say we have x-axis, and let's say we have first object with mass m1, which moves with velocity v1. It's a vector. And let's say second object with mass m2 moves with velocity v2. So before collision I stands for initial, right? And after the collision, let's say we have the same coordinate system, right? X, and this is final F after the collision. Let's say after collision, we will have slightly different situation, right? So let's say this is m1 moves with velocity v1 prime. Prime we usually use to denote quantities after the collision, right? And let's say the second object now with still the same mass m2, but moves with velocity v2 prime. Okay, so now I'm going to use this picture, and I start introducing refreshing recent material. So first of all, we can introduce total linear momentum. So now we have a system of two objects, m1 and m2. So first we can introduce total linear momentum, P capital. Of course it will be a linear momentum of 1. You see there is no bar underneath. It means it's small p. Right? Small p describes linear momentum of one object. And plus v2. So that's total linear momentum. Then, at some point we decided, let's look at the rate of change of the total linear momentum, right? So, rate of change of the total linear momentum, you see it's P capital, and rate of change is the dp over dt. And we realized that which forces are left over here? Only external forces, right? Internal forces gets cancelled. Which internal forces I'm talking about? Here, during the collision. Of course, m1 will exert force on m2. And at the same time, m2 will exert force on m1 during the impact, during the collision. Those forces, internal, cannot change the total linear momentum. Those forces are incapable of doing that. Only external forces can do. So in order to change total linear momentum, there must be some external force acting on the system. Right? So I will write net external force. You know what? Since it's in x direction, let me use just that one dimensional. I'm not going to consider vector two-dimensional case. Just one dimensional. So let me just use x, subscript x. And here also. Okay, so, and let me write, so the internal forces, which way I wrote, internal forces are out. The internal forces cancel each other. Cancel each other. Okay, so the external forces only present. And consequences out of this. If the net external force equals 0, what's the consequence of that? Linear momentum is conserved, constant, right? So let me write our conclusion. If net external force in x direction, right, in this case, of course, if you want to consider y direction, of course, you will have to do exactly the same for the y direction. You just need to look at the net external forces in the y direction. And if this guy is 0, then of course px must be constant. Must be constant. So capital Px equals constant, which is conservation of linear momentum. Conservation of linear momentum. Okay, so let me write this way. So for this case, Px initial equals to the B capital X final. So total linear momentum of this system before collision and total linear momentum of the system after the collision. So let me write it explicitly in terms of MV, MV, MV. Yeah, boy. I'm using linear momentum, but I did not write what is linear momentum by the no, I did write. It's over here. I'm losing my mind. Okay. Okay, so I can write M1 V1 plus M2 V2 equals to M1 V1 prime plus M2 V2 prime. So conservation of linear momentum applied for this particular system. And of course, if we know, for example, problem gives us that this object, for example, moves to the left, and since my x-axis, positive x direction that way, of course, when I write this equation, here I should have written minus. Right? So if we choose that way, then here I would have minus. So we have to keep track of the directions. And and now a few words about terminology. Let me put here a new bullet. Elastic collision. It's just very recent. In a previous recitation class, we were talking about this. Elastic collision. What can we extract out of these words immediately? What is conserved? Mechanical energy. Elastic collision, mechanical energy is conserved. So it basically means during the collision, I forgot to take the second wall, right? During the collision, of course, the object gets distorted, right? But then shape of both objects gets restored, right? And the whole energy is preserved. So of course, in that case, objects must be made out of proper materials, right? They must be made out of, I don't know, some special steel, right? Stuff like that. Elastic, if somebody tells that writes in the problem collision is elastic, it means proper materials were used, right? And it means that mechanical energy is conserved. Elastic collision. Mechanical energy is conserved during the collision, right? So first, a couple of words about dot product. Let's say we have these vectors, right? Let's say we have vector A, right? Let's say magnitude of 4 and vector B, and the length of this vector 2, and the angle of this angle is 60 degrees. So we need to find the dot product or scalar product, A dot B. First of all, is this the correct angle to use in our dot product? Yes, because both tails of both vectors are positioned at the same point, right? So that is the correct angle. So of course, in this case, we have to just write magnitude of A, magnitude of B, times cosine of this angle, which is 60 degrees. So it's a 4 times 2 times cosine of 60 degrees. Cosine of 60 degrees, I know by heart. It's 1 over 2. It's 1 over 2. That's why I picked that angle, because I know the value. Right. Yeah. So it will be 4. No, I know the values of both cosine and sine. So 0, 30, 45, 60, and 90. It's easy to remember. Then, okay, now let's look at this case. Let's say we have vector B, let's say magnitude of 2, and vector A, right, let's say magnitude of 4. And let's say this angle is 60 degrees. Again, dot product. We need to find the dot product. A dot B. Again, it's the magnitude of A, magnitude of B times cosine. Cosine of which angle? Is it 60 degrees? No, of course not, right? Because again, you need to position tail of vector A and tail of vector B at the same point. Basically, you can do it mentally, or you can actually redraw it. Vector A, you can position it like this, right? If you preserve the magnitude and direction of the vector, you can move it. So if you move vector A over here, right, and this will be our correct angle. So that is angle theta which we need, right? So in this theta equals, okay, I will just use theta, and then I will put numbers over there. So that is the correct angle. Don't forget, we will be using this rule many times in physics 1 still, and then when we go to physics 2 still, we're going to see these dot products, dot products, and then vector products, pretty much the whole semester. Next one. Sooner or later, you will remember it. So now, which angle? 120 degrees, right? 120 degrees. So it will be 180 minus 60 degrees, right? So that's angle, that is the angle, let me put it this way. So this is our angle theta. So cosine of 120 degrees, I also know it is minus 1/2. That's why I used it. So it will be 4 times 2 times cosine of 120 degrees, which is minus 1/2. So it will be minus 4. Now minus 4. Okay, I just wanted to remind you about this rule, how to find the correct angle. So next, now let's start using energy approach. Let's start using energy approach. Let me, or maybe I will just erase this part, right? Can I? Guys, start erasing this part. You guys good? So, I don't want to move camera again. So I will just put a new bullet, right? And so let's calculate work. So we have some object, I don't know, some car or some box being pushed over a certain distance. Distance is given. Force is given, and also it's given how force changes with this position, with distance, right, with displacement. So we have an object, and we have a force given, right? So let me draw it this way. So this is force, of course, in newtons. And we know how it changes with x. So first I will draw the curve, and then I will label the x and y axis. It's easier. So first it goes up, then it stays constant, then it goes down, stays constant, and then dies out. And now I will label points. So first here it's 400 newtons. That plateau, this point is, I think, negative 200. Yeah, negative 200. Here. Now position. This point is 3. All right, this point is 7. All right, then this point is 10. And this is 12. This point is 14, and this point is 15. And between them there are corresponding number of dots. Right. So we need to calculate the work. So this force, so we need to calculate work. Work done by this F. Which part is missing in the question? Right now the question is not complete. Something is missing. What else do you need in order to calculate work?
Mass.
Over which distance? Right? Force acts from 0 to 15 meters, right? But if the question is, of course, find the total work, yeah, you will calculate the work over the whole displacement from 0 or the whole displacement of 15 meters, right? But sometimes the question can be, what's the work done by the force as the object as this object moves from this point, for example, to 3, or to 7, or from 3 to 12, or from 7 to 14, right? So every time boundaries must be given, right? Boundaries must be given. So let's calculate work done by F over this stretch from 0 to 10. Right. Okay, let me ask you first. Can we use this formula? What, no? Yes? Of course not. Because here, if F is constant, yet this formula can be used, right? But in this case, force changes with displacement. So, of course, we have to calculate area, right? We have to calculate area. Or if you're comfortable with integration, you can write down functions and integrate it, right? It's pretty much will be almost as simple as to calculate area. So in this case, yeah, so we have to calculate this area. Okay. So this area, that's what we need to find, of course. Right. So I will write work. Which way I should label? I'll probably label it like this, in a bracket from 0 to 10. Okay, it's a trapezoidal shape. Of course, you can split. You can calculate area of this triangle. This triangle is exactly the same, right? And then area over rectangle. I will just use the formula for trapezoid, right? So which is 1 over 2 base 1 plus base 2 and times the height, which is missing. Right, so which will be 1 over 2. Base 1, it's this distance, right? So which is 10 meters. Then this base is 7 minus 3, 4. Right? And the height is 400 meters. So it will be 10 meters plus 4 meters and times height is 400 newtons, right? And the answer will be 2,800, right? Yeah, 2,800. Units. What are the units of work? Joules. Of course, joules. If you don't remember on the exam, at least write whatever you see in the formula. That will be correct, right? You can fight for your points, right? At least write Newton's times meters, right? But of course, it's better to remember. In that case, it will be difficult for me to fight against what you wrote. Okay, then let's calculate work, total work from 0 to 15. So now we need to calculate the total area on the total curve, right? So now we need to add this part. This area, is it going to be positive or negative? Negative. So in this case, we will have to subtract this area from that area, right? Okay, so now, you know what, let me label these points, right? O, A, B, C, D, E, and this F. Okay, so now, of course, again, it's an area, and let me write area of OABC minus, you know what, I will put plus, but of course area will be negative, right? Let me do this in this way, right? So more general, if I write it in this way, it will be more general. Area plus CDEF, CDEF. And of course, one of these areas will be positive. We already calculated it. So this is 2,800 joules, because we already calculated. So let me show that. So this. And this area, again, it's a trapezoidal shape. It has a trapezoidal shape, right? So we can use exactly the same, right? So it will be plus 1/2. This base, 15 minus 10, so it's a 5 meters. And this base is 14 minus 12, right? It will be 2. Plus 2 meters. And times height, and height, of course, now negative 200 newtons, right? Of course, it will be negative 2,800 joules minus 700 joules. I just carefully look at my notes. Yeah, it's actually quite simple. 2 and 2 gets cancelled, and you have 7 times 100. So it will be 2,100 joules, right? So positive work is done. Okay, what happened with the velocity of the car after this influence from the outside world? What happens with the velocity? Well, let me ask you first, what happens with kinetic energy? It went up.
No,
You didn't?
I didn't say that.
Okay, my lip reading is quite bad, right? Especially in English, right? That in Russian or Ukrainian language, right? English, of course, is much worse. Work kinetic energy principle. We calculated work done by that force on a certain object. Maybe, I don't know, some box was pushed, or the car was pushed, right? Or anything. And since, where is it? I lost. Yeah, here. Since work is positive, it means that kinetic energy went up. Final kinetic energy is larger than initial kinetic energy. So with this force, we dumped a certain amount of energy into the system, right? As a result, kinetic energy went up. Of course, it will be moving faster. If this energy was negative, of course, it means energy was taken from the system and dumped into the outside world. Make sense? Okay, we've already solved these problems in the past. Just refreshing it. Good. Now, so we just calculated, use this trick how to calculate a work. Now, let's use this. Let's look at those examples. Let me separate it like this. Right. So mass is 380 kilograms. So this ramp or the inclined plane, okay, let me make it not as steep as I was planning first. Angle of inclination, which letter is theta? Let's say theta is 27 degrees. And the whole length of this ramp is 3.9 meters. So let me write it over here. You know what? I will give that information in a minute. So piano. Okay, I don't care about the piano. It will be a box. It's difficult to draw. I can draw a person, right? But not a piano, right? Then, of course, here we have a person. Where it's too far. Okay, I will make his arms long, right? So that's the person, applies force. Of course, when you do this, of course, most likely you will apply along the inclined plane, right? Most likely. So let me draw this force. So that's the force you apply. And the value of that force is given. No, we'll have to find it. We'll have to find it. Okay, so that's and let me draw a displacement. So piano is taken from the very top, and of course we have to bring it to the very bottom. So displacement is from this point all the way to the very bottom. So let me draw this displacement. So that is S, and that is 3.9, I think. Yeah, 3.9 meters. 3.9 meters. Okay, it's actually vector. Right? It's actually vector. Okay, now everything what is given is on the board. So what we need to calculate first in part A, we need to calculate the value of that force, right? And a very important piece of information, right? So we assume that velocity is constant. Velocity is constant. Yeah, I think that's. So we need to find the force first. Since we're going to use energy approach, but also at the same time a little bit of Newton's second law approach, let me introduce first coordinate system. Right, I will introduce this way. This is y, and this will be my x. So let's find the force. I will apply Newton's second law quickly because it's from our past, right? I'm sure that you know how to apply Newton's second law. So let me do it. Let me apply Newton's second law in x direction. Right. So net force in the x direction equals mass times acceleration in the x direction. Old form of the Newton's second law. What's the acceleration in the x direction? 0. Velocity is constant. This acceleration in the x direction is 0. That's what this guy does, right? He takes care of that. So this is 0 since v equals constant. Wait, S is missing. Constant. Okay, so I can write. You know what? Before I can write, of course, I need to draw the rest of the forces, right? So let me draw this force, gravity. Then there will be normal force. I'm not asking you because we've done it so many times in the past. We assume that there is no friction. Right, no friction to simplify life. Right. So that's it. Okay, let me decompose this mg. Of course, this will be my x component. Of course, this will be my y component, right? And let me ask you, what's the value of this angle? You see this small angle? Theta. Again, we've done it in the past. You know probably geometry, which geometry you have to look. All right. So this angle is theta. Then, so what's the value of this x component of the gravitational force? mg times what? Sine. Look, we are talking about this side, right? But also I can draw it here, right? This and this, they are the same, right? It's a rectangle, right? So this side is opposite to the angle which I asked you to give me, right? So of course it's a sine function must be used. So it's mg times sine theta. So this is mg times sine theta. Of course, occasionally we still need to use Newton's second law to find the normal force or to find x component of gravity. Right. So that still should be close to the top of your head. Right? So And so if I write down this net force, this component of the gravitational force, is it positive or negative? Positive, right? Because it is in the positive x direction. So it is mg sine theta. And what else in the x direction? This force from the guide. Right? And it is in the negative x direction. So I have to introduce it into the equation with minus. And it is equal to 0. It's a past, right? That's what we had in our first midterm exam. Okay, so from here, we can calculate the value of the force that the guy has to apply in order to move the piano with a constant speed, right? With 0 acceleration, right? It will give him, it will require less efforts from him. So it will be mg times sine theta. Okay, you can plug numbers, mass is given, g, of course, you know, angle is given, no problems. It will be 1691 newtons. Right. Okay. These are preliminary steps. Now, what's next question? We need to find work done pretty much by all these forces. Let's start with the work done by which? By the man. So B, work done by this force F, basically by this guy. What's the work done by this guy? So, what can be used? Can we use this formula? Yeah, because the force is constant. If the force is constant, we can take a dot product between the force and the displacement, right? And this force guy applies, and it's a constant force. That force is a constant one, right? So, yeah, we can use. Right? So, work done. Again, I'm emphasizing that the difference between this situation and this situation. Here, force was not constant. As a result, we had to calculate area instead of taking the integral. Here, force is constant. We can simplify our life. You can still calculate using area because the force is just constant. It will be area of rectangle, right? So it will be F dot displacement. Every time when you solve problems like this, make sure that there is a displacement vector on your diagram. And force is also shown as a vector. So you can see which angle is between these two vectors. Because I saw on the quiz, students struggle with finding the right angle because I see mainly because vectors are not on the picture. Everything must be in front of your eyes. So, of course, by definition, it's Fs times cosine. What is the angle between these two vectors, force and the displacement? 0? Is it 0? What? 180. Is it 180? Yes, of course. Look, S is down the inclined plane, right? And F is up along the inclined plane. So, two vectors, one this way, one that way. So the angle between them, of course, 180 degrees, right? 180 degrees. So it's a cosine of 180 degrees. Of course, -1, -1 value of cosine of 180 degrees. Numbers, of course, force we found, so you can plug it. Displacement is 3.9. You can calculate it, and of course the work is negative. Because yeah, this guy is taking the energy from the system and dumping it into the outside world, right? Because he's slowing down system, right? And so gravitational force is trying to add energy into the system, and the guy, of course, is trying to take that energy out of the system and safely, to deliver this piano safely to the ground level. So if you do these calculations, you will get minus 6595 joules, right? Okay, you can round it off, but for now I don't want, because it's not the final result. Okay, so now we need to find work done by the gravitational force. Okay, I drew gravitational force, and now let me write some work done by this gravitational force. Of course, gravitational force is a constant force, so we can use a dot product between the force and the displacement. So Fg dot S. Okay, of course we can open it up, and explicitly it will be mg times S times cosine. Now the question, which is the correct angle between these two vectors, force of gravity and the displacement? Okay, and it's not this angle, so we need to look carefully at the picture. So you remember, in order to find the correct angle between two vectors, you need to position their tails at the same point, right? Their tails at the same point, and then the angle less than 180 degrees is the correct angle. So in our case, gravitational force, this, we slightly erased it. Then displacement, it's over here, but I can draw it over here, right? So to make it easier. So that is my displacement. All right, yeah, compressed it slightly. So, strictly speaking, that is the correct angle that we have to use in this dot product. So you see the tail of vector S at this point, the tail of vector mg also at this point. So that is the correct angle, right? So, and of course we can find this correct angle, the value of this angle, by looking at this triangle. So this right triangle, because mg is straight down. This angle is 90 degrees. So if this angle is 90 degrees, then of course this angle will be 90 minus theta. So let me write here, it's a cosine phi, and let me open my explanation box. So phi equals 90 degrees minus theta, which is 90 minus, I think the angle, what is 27? Yeah. 90 degrees minus 27 degrees, that will give us 63 degrees. And yeah, so from that triangle you can see. Okay? So now, if you put all numbers, right, I'm not going to do it. I will just write down the answer. Right. Everything is given, all the numbers, displacement is 3.9, right, and so on. So if you, okay, maybe I will write this, mg cosine of 63 degrees. So if you plug numbers, you will get, where is it? Yeah, 6,595, that's work. It means units of joules, right? So we found the work done by this guy, by this constant force F. Right? Now we found work done by the gravitational force, and the last force, which is still present on the picture, work done by the normal force. But we all know that work is zero because displacement and the normal force are perpendicular to each other. But anyway, let me write it. N dot S, of course, that N S times cosine of 90 degrees, of course, which is zero, right? Right, so now we know all works. So the next question in part D, right? So we need to find the net work. So we have, we just need to add all the works together, and the problem is solved. Right? And the problem is solved. So now W net is equal to work done by F plus work done by the gravity plus work done by the normal force. That's it, right? Yeah, three forces. Right. And of course, this is zero, right? So it will be this work done by the guy. Of course, the work is negative. Right? The work is negative. Calculated. It's minus 6,595 joules, and work done by the gravitational force 595 joules. And of course, that is 0. And it's not by accident this network is 0. We could have predicted it from the very beginning, right? Because velocity, right, we wrote it down. Velocity equals 0 as piano slides down. So this guy takes care of that. He guarantees that velocity will be constant, right? It means acceleration is 0. But what I wrote, velocity equals 0. Velocity equals constant. Some constant value, right? And if you recall work kinetic energy principle, work equals to delta K, right? Work kinetic energy principle. Since velocity is constant, so kinetic energy at the initial point, at the final point, and throughout the whole motion is exactly the same. Kinetic energy is the same. Mass constant, velocity constant. Of course, kinetic energy is constant, right? So it means that delta K equals 0 and work equals 0. So whenever you see a system which moves without acceleration, with constant velocity, you can tell immediately, network must be 0. Right? The network must be 0 whenever you see a system which moves with the constant velocity. Again, it's a network is 0 because these individual works, of course, they're not 0. But if you add them all up, you must end up with 0. Okay, cool. So now, done. Okay, so we have a spring. So, and some object. All right, so first we compress the spring, then release it, right? So the level of compression is given. We will have to find velocity of the ball when it's about to leave the spring, right? And then we will have to find the height, the maximum height the ball can reach, right? So let me erase this. Can I start erasing this? Yeah. So let me start with the pictures, with a picture. So we have a spring plus a ball, right? So that will be our system. And so let's say this is ground, right? And let me start with spring which is relaxed. So when the spring is relaxed, it is. And let me position it in some sort of barrel, right, cylinder, so that it wouldn't be moving from side to side. So here it is relaxed. The spring is relaxed. So this is the equilibrium, right? Then compressed. Let's say here it is compressed. Right, so the same cylinder, right? It is compressed, and here is the here's the ball. Right. So we compressed it and then released. So initial velocity of the ball, right? Let me label this level as level 1, this level as level 2, and of course here the ball will be about to leave. So we need to find first of all this velocity, v2. Right? When it's about to leave the spring is relaxed now after decompressing itself. Right. And the third level I will introduce in part B. Right now, this is enough. So what else is given? Compression. The level of compression is given, right? So this is x, and I don't remember the number. 0.16 meters. 0.16 meters. Compression is given, x. because that is a distance from the equilibrium level. This is the equilibrium point, right? You're right. And K, spring constant is given. K, it's a large number, 875. 875 newtons per meter. So spring constant of the spring is given, right? Yeah, and mass of the ball is also given. 0.38 kilograms. So what do we need to find? We need to find, so in part A, velocity 2, when it is about to leave the, yeah, it's more convenient, 0.16 meters, 0.16 meters. Okay, let me add here, x equals to 0.16 meters. Yeah, that's it. Yeah, nothing else. Okay, so which approach should we take? Yeah, of course, we're all discussing energy approach. So of course, I will force you to use energy approach, right? And in the exam papers, I actually near each problem I write use energy approach, use work approach, use whatever. But of course, if you need sometimes, for example, like find the friction force, of course, I assume that you will be using Newton-second law quickly, right, in order to find the value of the friction force, right? So, forces, air resistance can be neglected, right? So that's the only source of losses, energy losses, right? Spring force, is it conservative force? It is conservative, and as a result, we can introduce potential energy, spring potential energy, 1/2 kx squared. Then, what else acting on the system, on the ball in this case? What, any other forces? Gravity. Again, gravitational force is a conservative force. Again, we can introduce corresponding potential energy, mgy. Right. Okay, so, and nothing else, so no losses in of energy, so it means we can use conservation of mechanical energy, right? So let's use conservation of mechanical energy. Conservation of mechanical energy. So it means that we compare energy at level 1, basically point 1, and point 2, level 2, right? So we'll just compare E1 and the energy at point or level 2. So now, of course, let me write explicitly. One object, so it means one kinetic energy. And how many potential energies? 2. Okay, all right, so let me start with spring. U spring 1. Right? Plus U gravitational 1. Then equals kinetic energy at second point plus spring potential energy at second point plus gravitational potential energy at second point. Now, after this, what will be my next step? Because I wouldn't be able to move any further if I don't make that step. I have to introduce something. I have to show something in the picture, right? The reference level. I need to know where is my gravitational potential energy 0. We don't have that freedom with the spring potential energy. Every time spring potential energy is 0 at the equilibrium, where the spring is relaxed, right? But for the gravitational, we have to show. I think I picked at the level 2. Let me check my notes. Yes, I picked here. Let me use this. UG equals 0. So that's my reference level. It's up to you, right? It's not the only level. You can use this level. Maybe this will be more convenient, right? I found somewhere in the middle because there will be third level. I decided to use it in between. Okay, so now let's dump zeros. What is 0 in this case, in this equation? K1? Yeah, because the ball was released. So let me write, so V1 equals 0. So we compressed it, and then quickly remove the hand, right? And of course, initial velocity is 0. So K1 is 0, right? Then, what about, what else? What about this spring potential energy? 0. Because now the spring is relaxed. It's not capable of showing any potential, right? So now it is relaxed. So displacement from the equilibrium is 0, right? Maybe I should write the formulas, right? So UG equals mgy, and U spring equals 1/2 kx squared, right? So for the spring, when the object is here, so compression is 0, so potential energy is 0. So I can dump this as well. So now the spring is relaxed. Spring is relaxed. X equals 0, right? Then, gravitational potential energy at second point, at the second level, 0. Because, I forced you to use this as the reference level, right? If you pick this reference level, of course, this term would be 0. But in my case, this is 0. Reference level. Okay, so we cannot simplify it any further. I think that's it. So, 1/2 kx squared, 1/2 kx squared. Gravitational potential energy, positive or negative at point 1? Positive or negative? Negative? Negative. True? Yeah, of course it is negative, right? Because at level 1 is below level 2, right? So whenever it's below, potential energy is negative, right? So of course we have to put minus manually. So it's a minus mg. And what's the y in this case? What's the value of y? It's x, right? In this case, it is x, 0.16, right? This distance between these two levels, it's a compression of the spring, right? So it is minus mjx, right? Then K2, that's where our unknown is, V2 squared, right? So that's my, okay, I need to disconnect this arrow from this because it might cause confusion. And so that is the question mark, right? That's my question mark. Yeah, and these are zeros. Okay, basically, how many unknowns do we have? K given, X given, M given, given. One unknown, one equation. Okay, problem is solved. This part of the problem is basically done, right? So we just need to solve it for V2. V2 equals square root of 2 over m. Again, I will just take this 2, bring it upstairs. This m goes downstairs, right, on the other side of the equation. So it will be kx over 2 minus mgx. Of course, you can factor out x, for example, or you can do whatever you feel like doing, right? Now it's just simple algebra. And so the answer is, again, if you plug everything, you will get 7.47 meters per second. Of course, you can approximate it as 7.5. I mean, round it off. You can round it off to 7.5 meters per second. Good. Again, what's the beauty of energy approach? You don't care about the history of the motion. What you care only about the initial and final point. You don't care what system does between those 2 points, right? So system might, I don't know, object might go something like this, right? But you don't care. Energy approach, you need to know only the values of something at the initial and final point. So now, next question, let's find the maximum height very quickly. Now, part B. So So let's find maximum height. And let me label it. First, let me draw. So it will go, for example, let's say to this level, right? And we need to find this h. So now let's find the h. Again, now spring. Is spring in the game? Now the spring is out. We can forget about that, right? So now it's just a ball with its kinetic energy and the gravitational potential energy. So we have only one potential energy and one kinetic energy, right? So again, now I will just use conservation of mechanical energy. And now I will be comparing total mechanical energy at level 2, at point 2. And let me label this as point 3. Right, so, okay, let me write it here. So this is the level 3. Right, so it will be E2 must be equal to E sub 3. Conservation of mechanical energy. So now let me write it faster a little bit. So it will be K2 plus U gravitational 2 equals K3 plus U gravitational 3. What can you tell about kinetic energy at the point 3? 0, because it will stop for a moment, right? At the maximum height, of course it will stop for a moment. This is 0. V3 equals 0, right? So let me write V3 equals 0. We know from the physical situation that. Then, what about this gravitational potential energy? 0, because that's my reference level, right? I forced you to use this gravitational level, this reference level. Okay, so, this line is almost missing, I even didn't see it. So now we just need to compare kinetic energy with this potential energy. So 1 over 2 mv2 squared equals potential energy positive. Is potential energy positive at point 3? Of course, yeah, because it's above the reference level. So it will be mgh. And h is the distance between the levels, between level 2 and level 3. Okay, so V2 we found, so we can get h easily. H would be equal, m can be cancelled. Right, we can do our small mass destruction, right? So it will be V2 squared over 2 times g. V2 we found, just divided by 2g, squared velocity divided by 2g, and you will get 2.84 meters. So that's the distance from level 2, from the equilibrium level. If the question is about find the distance from this level, you can add slightly. Okay, again, I'm emphasizing that when you use conservation of mechanical energy, you don't care about what happens between the initial and final point. You just need to know the values of initial and final point. Because there is another example, I'm not going to discuss it, but you can see it in my, when I sent you a file. Okay, questions? Anything? Now, if you don't have questions, let's move to this linear momentum, impulse, and then collision, a little bit of collision. So pretty much maybe 2 problems, maybe. So, right, so it will be already a couple of hours. Wow. Time flies. All right. Can I start erasing this? Good? Okay. All right. So now let's review idea of an impulse and how that can be used to calculate the final velocity or change in the velocity of the system. So I'll put a new bullet. So now let's review impulse. I will probably draw the picture first. So we have an object which moves under the influence of this force, force in newtons, and is given versus time in seconds. Right, so this point 1, 2, 3, 4, 1, 2, 3, 4. This point is 4. This point is 2. And let's say this is our curve. That's how force changes with time. That's how force changes with time. And so we need to find the change in the velocity, delta v. So over here we had some, at this moment of time we have some one velocity, then there will be, after the influence of this force over this stretch of time, velocity changes, so we need to find the change in the velocity. What else is given? Mass of the object is 5 kilograms. Right. One-dimensional motion, of course, and force is given, right? Okay, so now let me draw the physical situation. So let's say we have this x-axis. We have some object. Well, which object I drew? Okay, I just drew a box on the wheels. Okay, so let's say at this point, okay, I'm plotting x. Here we have versus time. This is graph how force changes with time. Now I'm basically drawing a physical situation, right? So in space. So let's say at this moment of time we have velocity, time, this is the moment of time, 1 second. Right? And let's say this is the moment of time, t 3 equals 3 seconds. So this point is over here, this moment of time is over there. So what can you tell about velocity? No, first of all, what can you tell about the force acting on the card over these, at these points? 0, right? Over here, force is, let me use the red, right? Black is, let me use red. So here, force is 0. So as a result, velocity, constant. Velocity must be constant over this, before this moment of time, all this time from 0 to 1, velocity over here is constant. So let me label it as v1, and it's a constant, right? So here, over this, what happens with velocity? It will be changing, right? Or it changes. And can you tell me, is it increasing or decreasing velocity? So first, can you tell me, this force, does it act this way or that way? On the graph, velocity, forces are positive. It means it acts in the direction of motion, right? So it means that velocity will be growing, right? So here velocity changes, right? V changes, right? And over here, V2, of course, will be again constant. Different constant. Okay, let me use this constant 1, here constant 2, different constant, right? And here, velocity will be changing, right? Because of this force. And let me draw that this force is F over here in the positive x direction, right? So this force is over here. And so this is plot in time, and that's what we have in the real world. And so what we need to find? We need to find V2 minus V1. That's what we need to find. So this is V2 minus V1. That's what we need to find. Okay, so now since we have information how force changes in time, it's a direct indication that we have to use momentum principle. Where is it? Here, momentum principle, right? Again, the idea is very similar to the work kinetic energy principle, right? So before work, what's changing kinetic energy, and now impulse changes linear momentum, right? And of course, velocities are inside of this linear momentum. So let me separate it like this. So J equals delta P. I dropped vector sign because everything in the x direction. I can put actually subscript x, x, one dimensional. Okay, how can we calculate impulse? Area under the curve. Force is not constant, of course. We have to calculate area under the curve, right? So Jx, it's an area, right, under F versus time. Right? In our case, let me label these points, I don't know, A, B, and now let me draw this vertical line, point C. So I will just take this area and multiply it by 2. Right? Take this area and multiply it by 2. Although, yeah, I can use just 1/2 of base times height still. Okay, anyway. So it will be 1/2. Oh, 2 times and 1/2. Base is 2 minus 1, which is 1 second, times height of 4. Okay, this is 4 newtons. 4 newtons, right? So it will be what? 4 newtons times seconds, right? 4 newtons times seconds. And delta Px, it's mv. Okay, let me use first p sub 2 minus p sub 1. Right? These steps are usual, so I'm not asking. I mean trivial, so I'm not asking. Change by definition, it's a value of something at the final point minus value of this something at the initial point. So it's mv2 minus mv1. Mass of the card, of course, doesn't change as we push it with this force. So m can be factored out, and we'll have delta v. That's our unknown, right? So just let's put it all in the momentum principle. Right. So it will be m delta v equals jx. So delta v equals jx over m. Jx we calculated. M. I know mass is given. Yeah, I wrote it down. It's 5 kilograms. So it will be 4. Is it correct? Let me check. Yeah. 4 newtons times seconds divided by 5k. So it will be 0.8 meters per second, right? Yeah. Well, yeah. 0.8 meters per second. Okay, it's enough, right? Again, idea is very similar to idea of work kinetic energy principle. Work will change kinetic energy. Impulse changes linear momentum. Usually students, so we are more familiar with work kinetic energy principle, but with this idea is the same, but we're just less familiar. It's so not so intuitive. It's just a question of getting used to it. Okay, any questions? Let me check if it's still recording, right? Yeah, still alive, cool. Now, last, or if you feel strong, we can look at 2 problems, but we'll see. Now, collisions. Let's look at these ideas. I will erase probably this part now. Now it's fresh. We just discussed these problems in our previous recitation class. Again, two-dimensional collisions are not going to be on the exam, right? Only one-dimensional collisions, right? Next problem. It's about a bullet hitting a wooden block, and the wooden block is attached to the spring, right? So initial velocity of the bullet is given, then masses of bullet and the block also are given, and we need to find velocity. Yeah, and the bullet gets embedded into the block, right? So we need to find the velocity of the block with the bullet inside right after the impact, before the spring starts being compressed. Okay, so let me draw the situation. So what we have here a bullet plus a wooden block and plus a spring. Although this, what is our system? This is our system. Spring is not part of the system, right, which we're trying to describe. Let's draw the picture. So we have a wall, horizontal surface, the floor, all right, and let's say this is our initial situation, or let me call this situation, yeah, let's say initial situation. Then we have a spring relaxed, and let's say we have here our wooden block of mass M capital, I think. Yeah, mass M capital, right? And here comes the bullet. Small bullet with mass M and velocity, I think I label it V. Yeah. Of course, velocity of this block initially is 0, right? So that's, oh, everything's flying. Now, spring constant, of course, is given. All right, so let me write down what is spring constant. Spring constant is 2000 newtons per meters. Yeah. And in this initial situation, of course, the spring is relaxed. And this surface, we don't have any friction between the block and the floor. Okay, we will need coordinate system because we will have to work with vectors, right? So we have to introduce coordinate system, and since bullet flies that way, of course the block will be moving that way. It makes sense to introduce to align x-axis to the left. So let me do it this way. So that is my x, and of course that is my x equal 0. That's my origin at the equilibrium. Then final situation for the impact. So exactly the same. So now let me label it with F, which means final. And now the spring is still relaxed, but now the bullet made a hole, and now the bullet is inside. And yeah, of course, mass of the block is still the same. We will neglect some loss in the mass of the wooden block. Right? So, yeah, and what we need to find, of course, we need to find this velocity. I will label it as V sub 2, right after the impact. So right now, the spring is still relaxed. The spring is still relaxed. Okay, so I think that's the physical situation. Yeah, I did not give you numbers. Yeah, let me write velocity of the bullet before the impact, 300 meters per second. Then mass mass of the bullet, 30 grams. Let me convert immediately to kilograms, right? It will be 0.03 kilograms. And mass of that wooden block, it's not that heavy, 1 kilogram only. Yeah, spring constant I gave, velocity here. All right, okay, yeah, everything's here. So, which approach to take? Let's try to use laws of conservation. First, is mechanical energy conserved? Right, the first, let's check that. And mechanical energy is not conserved. Why? Because we damage the, objects damage each other, right? So bullet bullet made a hole into this wooden block, right? It means damage has been done on the wooden block. And of course the bullet will be also probably to some extent distorted, right? So of course it means that some energy will be spent, right, to create this damage. Right? Okay, so it means that mechanical energy is not conserved during this impact, right? So, okay, let me separate this. So first we need to find this, right? And first attempt we want to try is mechanical energy conserved. And I'm telling you, mechanical energy is not conserved. Right, so we cannot use this. Right, then, of course, this collision, right, is perfectly inelastic collision, right? Perfectly inelastic collision. Right. Mechanical energy is not conserved, and we can write this is perfectly inelastic collision. Perfectly inelastic collision. So objects stick together and move together with common velocity v2, right? Of course, during the perfectly inelastic collision, energy is not conserved. Never. Now let's check conservation of linear momentum. Forces in the horizontal direction, right? Friction is not there, all right? Then what else? Spring force. Spring force is possible, but right now during the impact, spring is not compressed. So spring force does not act on the wooden block with the bullet, right? So it means that net external force in the horizontal direction is 0. There are only those two candidates, right? And they're both 0. So it means that linear momentum in the x direction during this impact is conserved. So we can use conservation of mechanical energy. Let me write this down. So since there is no friction, plus F spring, which is equals to minus kx, equals 0, right? So I can write it means that the net external force in the x direction equals 0, and we can say that linear momentum, total linear momentum in the x direction is conserved. Right? So I can write that P, again, it's P capital, right? Probably I will write immediately, compare P initial in the x direction equals to the total linear momentum final and in the x direction. Conservation of linear momentum. Let me write conservation of linear momentum. Right. Okay, so now what? We just need to write explicitly total linear momentum before collision, total linear momentum after the collision, and see if that equation is enough to solve the problem. All right. So before, mass moves with velocity v in the positive x direction. So contribution to this equation is positive, right? So let me write it. No, I leave the space. So mv positive. Then wooden block of mass m and velocity v capital, but it is at rest. So let me dump this immediately. And after the collision, we have both objects move with the same velocity. Okay, let me first write them as two separate terms: mv2 plus m capital v2. But of course, v sub 2 can be factored out. Okay, so what we have? This is given, this is given, this is given, and one unknown. One equation, one unknown. Yeah, problem is almost solved. So let me continue that there. So it will be m times v equals m small plus m capital times v sub 2, right? So that is our unknown. So let's just solve it for that. V sub 2 would be equal m divided by the total mass of the system n times velocity. Right. So now you can plug numbers. I will just look at my notes. So the final result will be 8.74 meters per second. Okay, let me frame this. That is the expression, and that is the number. Right, so now that is part A, that is part B. Yes, so maximum compression. So now we need to find maximum compression of the spring, of course. So let me label it as X. So now the final situation will be, of course, something like this. Right? So the spring will be compressed. Here will be the box with the bullet. Let me align all these three pictures. Right? So, and that will be my compression, which needs to be found, right? Okay, I'll probably erase this and start moving over here to this side. Okay, so now let's analyze again which laws of conservation can be used. All right, let me try to bring this down. No, it doesn't help much.
That's fine.
Yeah. Okay. Is linear momentum conserved now? We just used linear momentum, but can we use it now? Why not? If we use it once, the chances that we're going to use it second time not very.
The spring's compressed.
Yeah, now the spring acts on the system, right? And spring is not part of the system. System, bullet and the wooden block, that's our system, right? So spring is an external object, right? So spring is an external object. So now when we're compressing this, spring force will be acting on this wooden block with the box, with the bullet, right? So now a linear momentum is not going to be conserved. Right? So now let me write first that. Right, so since F spring, which is equals to minus kx, is not zero, x now is not zero, because now we are away from the equilibrium. So now we're compressing the spring. So throughout the whole motion, there will be non-zero spring force acting. So as a result, F external in the x direction is not zero, and we cannot use linear momentum is not conserved. Linear momentum is not conserved. Mechanical energy, the last savior. Is that conserved? Is mechanical energy conserved? Now, what, we don't have friction still, right? Spring force, yeah, it acts, but it's conservative force. We can introduce potential energy, right? So, which leads to the conservation of mechanical energy. And the gravitational force is on the same level, so the potential energy due to gravity is constant, and we can make it zero, right? So, we can use conservation of mechanical energy. Mechanical energy is conserved. Conserved. So let's, which way label them? Again, just initial and final. Okay. E initial equals to E final. Of course, in initial I mean maybe F2 final 2 label this way. Running out of ideas how I can label these 3 stages. So this final, let me just write everything. So Kf plus U spring F equals to Kf2 plus U spring F2. Wow, it's weird notations, right? Never used this before. Right. Kinetic energy at this point, at the maximum compression, 0. It will stop for a moment, right? So Kf2, right? So this is 0. It stops for a moment. Then this spring potential energy, 0. It's not compressed at that moment, right? It's about to start being compressed, right? So this is also 0, not compressed. Compressed, right? Okay, so, and the rest, of course, not 0. So let's write explicitly. This is velocity v2 is involved, right? 1/2 k, no, k, m. 1/2 m v2 squared equals to 1/2 kx squared. Of course, x, that maximum compression, right? Let me write here that velocity. This velocity is 0 if I right. 1/2 goes, and we need to find x. Right. It's quite simple. So now x will be equal to square root of m over k v sub 2 squared. Of course, we can take velocity out of this square root sign, and we've done v sub 2 times square root of m over k. Right, so, oi! Okay, tell me where I made a mistake. I was afraid of that, right?
The mass should be.
Yes, masses. You should have started screaming immediately, right? Before I embarrassed myself completely, right? So of course this, you see, we have a mass of the bullet plus mass of the wooden block, right? So they're moving together. So of course that mistake will be not that significant, but still. M capital 1/2, right? Of course. Here mass small plus m capital, and here the same, right? M small plus m capital. Okay, so now if you plug it all, you will get approximately 0.2 meters. Okay, I think it should be enough, right? So we've been, what, for almost 2.5 hours, right? Slightly short. But again, it's not the record. Last year, preparing for the final exam, we were almost up for 2 hours. It was quite a marathon.